That should be okay. Whoa, I can hear myself now. Microphone's on.
All right, good afternoon, everyone. It's my pleasure to be introducing today's colloquium speaker, Professor Jason Wang, who's coming to us from Northwestern. Jason did his undergrad degree at Cornell before moving out west to UC Berkeley for his PhD, where he worked on directly imaging and characterizing planets with the Gemini Planet Imager. Jason then spent a few years as a 51 Pegasi B fellow at Caltech before starting his current position at Northwestern. Many of us will have probably know Jason from the amazing time-lapse movies he's created, and hopefully he'll show us some of these of the directly imaged planets, especially the ones around HR 8799. And Jason has been at the forefront of developing new instruments and techniques for directly imaging and characterizing exoplanets. So I'm sure we're all happy to hear his talk. Jason?
Thank you. I have my own mic, so thanks for that introduction. Thanks everyone for coming. Yeah, as Sam said, I'm going to talk to you about some new frontiers in exoplanet imaging, how we're able to, new frontiers to improve imaging itself so that we can do very precise imaging and dig these dark holes to see planets in reflected light. Also advances in moving to very high spectral resolution, spectroscopy of exoplanets, and also very high spatial resolution imaging of exoplanets. So I'll talk a little bit about all of these and how maybe in the future, these in future observatories and future ways could lead us to habitable worlds. So as any exoplanet talk, we generally start with the obligatory slide of all the known exoplanets. So this is probably a couple years out of date, but at this point it doesn't really matter. It's plotted on the y-axis, the mass, and the x-axis is the major axis, and it's color-coded by detection technique. You can immediately see that transits and radial velocity have detected a lot of planets. Microlensing detected a bunch more. And then in this little corner in the top right, that's where direct imaging is lying. We have a few planets over there. And direct imaging, why we haven't gone down in mass because direct imaging is just hard. So for the easiest planets that we can directly image, direct imaging is like watching a firefly circle a streetlight from several miles away. So that gives you a sense for the brightness ratio of the planet with respect to the star. And these are the brightest planets that we can directly image. And it gives you a sense for the angular separation, how far separated this very faint thing is from the very bright thing. So how do we do it? So here's a cartoon I drew for how do we image an exoplanet. So our goal is to image, right now, Jovian exoplanets next to their bright stars. We generally do this from the ground, although now we're doing a bit more and more in space. But generally, we have to contest with some sort of atmospheric turbulence. So to correct for atmospheric turbulence, we have to use some sort of adaptive optics system. It's basically like going to your optometrist, but instead of going every once a year if you're good, you have to go every millisecond, because that's how fast the atmospheric turbulence changes. After we correct for the aberrated wavefront, we have to then use a coronagraph or some sort of device to block out the glare of the star so then we can finally image the planet. So this is just a cartoon schematic. I'll just show you some reasons for why we need all of these subsystems. So this is an image taken from the 8-meter Gemini South telescope without adaptive optics turned on. This is an image of a star. So the star itself is a blob. So this is what's called a seeing limited image, where you're seeing the blur of the atmosphere. And this star looks like this giant blob. And then when we turn on adaptive optics, we can see that we can concentrate the light of that star into a very tight core. This is a diffraction limited point spread function. And then if you're looking very carefully, you'll notice that there's actually a second point source in the image. This is a binary star. So this binary star would have been completely hidden under the glare of the primary if we didn't have adaptive optics. There'd be no chance to see it here. We have to use adaptive optics to see that secondary star. And this is just a binary star. Planets are much fainter than this. So if a binary star can get washed out, the planets are completely washed out. So we have to have adaptive optics, something to basically correct for the turbulence in our atmosphere. But that alone doesn't get us to imaging planets. So here's a simulation of an image if we had a perfect wavefront, if we had no optical aberrations at all. This is an image of a star and a planet. But you can't see the planet. The planet is in the center of this image, but you can't distinguish it because we're still limited. Even there, we're still limited by the fundamental wave-like nature of light. The fact that light interferes with itself and creates interference ripples, the Airy disk, that basically prohibits us from seeing the faint planets underneath the diffracted light of the host star. So here we have to use optical elements, which we call coronagraphs, but there are other optical elements we could use to block out, to suppress the diffraction of the primary star so that we can then see the planet underneath. So like this planet is in this image, but no matter how hard you look, you're not going to be able to tell it was there until we use a coronagraph. So here's my test for you. So this is images taken by the Gemini Planet Imager. This is what state-of-the-art adaptive optics systems with state-of-the-art coronagraphs. And these are integral field spectra images. So for each image is actually animation scrolling through a bunch of different spectral channels in the near infrared. That's why it's an animation and not a static image. My challenge for you is, can you find the planets? On the left is Beta Pictoris b. This is like the brightest directly imaged planet. And on the right is 51 Eri b, is one of the faintest planets we've ever directly imaged. So can you find the planets in the image? Any guesses? You think it's this one?
That's the one. I want you to look at the right.
Any guesses here?
No.
No guesses? Well, you're correct. That is Beta Pictoris b right there. You're very good eye. So that is a planet. This is a trick question. No matter how hard you look at this image, you're not going to see the planet.
I got it right.
That's because even with state-of-the-art adaptive optics and coronagraphs, it's not enough. We often have to use additional algorithmic post-processing of the data. So what we have to do is something called stellar PSF, point spread function subtraction. So one of the common ways to do this is we observe our system with the derotator of the telescope turned off. So basically, the sky rotates due to the fact that the Earth rotates. Have you ever seen those time lapses of the Milky Way rotating over the sky? So naturally, we build our telescopes to kind of correct for that. But if you turn that off, you can actually, the sky will rotate over the course of the observations. So any real astrophysical point sources are actually going to rotate around the star. This is not orbital motion. This is just due to the apparent rotation of the Earth. Whereas the stellar diffraction pattern remains relatively static and not rotating in space, whereas the real astrophysical sources do rotate.
That's
so,
about half an hour or so?
Yeah, so this is about half an hour. Your mileage varies depending on where in the sky you look and things like that. But yeah, something like this. There are other things we can do, not just this, but this is just one of the common techniques and easy to visualize. And then when we do something like this, we have these images, and then we do some sort of sophisticated, fancy post-processing. Here we're oftentimes using something like principal component analysis to basically to separate out, it's kind of this blind signal separation problem, to separate it out, the diffracted starlight from the real planet. So on the top left, this is a frame of data. On the top right, this is the PCA reconstruction of that glare of the star. It's actually animation, but you can't really tell the difference. But if you subtract these two on the bottom left, this is data minus model. And you can see that as we increase the number of PCA modes, the amount of different patterns we're using to reconstruct the glare of the star, you can see that we're actually removing more and more of the substructure in the image. And then if you stack 55 of these residual images together and we increase the number of PCA modes, you can see that this faint point source that was otherwise hidden underneath the residual glare of the star appears in the data. So this ends up being a background star with a chance alignment. It has to be in chance alignment with the star we're looking at, but this in principle kind of gives you a sense for like why we need to do this to improve our sensitivity to see fainter point sources next to our bright host star. So the combination of all these things together allows us to get images of planets. And then if we take those images over time, we can actually make time lapses, like Sam mentioned. And these are the longest time lapses of exoplanets we have to date. So on the left, this is 12 years of data on the 4 planets orbiting HR 8799. These are all super Jupiters. These are like planets between 5 to 12 times the mass of Jupiter. But you can see these 4 planets are orbiting in a near face-on orbit here, you can see. On the right, this is the longest time lapse we have of any exoplanetary system. This is 17 years of image data on Beta Pictoris b, one of the first directly imaged exoplanets. It's on a near edge-on orbit. It's about 1 degree away from edge-on. So that's why it looks like it's moving in a linear line. So these are super Jupiters. What about imaging smaller planets? So we've done that once. So this is from the Voyager spacecraft. This is a picture of us, Earth. And I like this image in many ways, but one thing is that this is Voyager at 40 AU, and you can see the amount of diffracted starlight from our sun in order to see this this pale blue dot that is the Earth. We're now going to try to talk about, can we do this from about 5 orders of magnitude further away? You know, instead of our telescope being 40 AUs from the star, we want to be, say, tens of parsecs from the star, and be able to, again, discern that dot from all of this. And that's kind of where we want to go to. So here is kind of you'll see a lot of these plots, so let me just explain them. This is kind of our direct imaging, high contrast imaging kind of sensitivity plot. On the y-axis, this is flux ratio relative to the host star, so how faint is that point source relative to the main star you're trying to image. On the x-axis is angular separation, so how close to the star are you? This is the sensitivity space of all of our current ground and space-based high contrast imagers. We're imaging things about 1 million times fainter than the host star at about half an arcsecond away. That's kind of where we are. This is Earth at 10 parsecs, or this Earth around a sun-like star. It's, we're talking about a planet that's 10 to the 10 times fainter than the host star at an angular separation of about 0.1 arcseconds. And it's quite a big jump we're going to need to make to get down here. So that's what I'm going to talk about next is, folks have been thinking about this thing called Habitable Worlds Observatory and what science can we do down here. But the question is, how can we get down here? And that's where the Roman Space Telescope Coronagraph comes in. So the Roman Space Telescope has this wide field imager with lots of cool science cases, and that's not what I'm going to talk about today. We also attached onto the side is the Coronagraph instrument that's a technology demonstrator to basically, instead of going from 10 to the minus 5 all the way down to 10 to the minus 10, we want to go just a few orders of magnitude, say 10 to the minus 5 to 10 to the minus 8 or 10 to the minus 9, kind of demonstrate, do we know what we're doing so that if placed on a proper telescope that's dedicated to imaging Earth, we can actually reach these 10 to the minus 10 contrasts that we need to get to. Yeah, so I'm going to talk about the Nancy Grace Roman Space Telescope first. So here's a nice chalk walk art. I did not do this, but this is a cool chalk walk art in Pasadena of the telescope itself. It's coming surprisingly quick. I know, lots of people have been excited about JWST and now JWST Online and doing lots of cool science. The next one, the current nominal launch window, I think it's late 2026 to mid 2027. So if things go well, in a few years' time, this will be in space. So like I said, there's the wide field imager, which is the main part of the Nancy Grace Roman Space Telescope. But there's also a coronagraph, which is this part of the logo. And I'm going to talk about that part of the logo. So the coronagraph is going to be very important in that it's going to demonstrate a bunch of key technologies for exo-Earth imaging. These are things we've never done in space before that we think we'll need to do in space for something like Habitable Worlds Observatory in order for us to get down to those levels of sensitivity. The first thing, and possibly the hardest thing, is that we need to do what's called ultra-precise wavefront sensing. So even in space, there's no atmosphere. Just from the heating and cooling of optics and the breathing of optics, you have optical aberrations that kind of drift over time. And we need to sense and correct for those down to about the 10 picometer precision. So that's like a fraction of the size of a hydrogen atom, just for a sense of scale for how precise we need to sense our optical aberrations. we'll be doing this in an interesting loop where the telescope is going to sense the wavefront errors. That data is going to be sent all the way back down to Earth. We're going to make corrections and send them back up to space. And so this is the first time we're doing something like this, so the ground is going to be in the loop. But maybe in the future, once we have these things more robust, for something like habitable worlds, we don't need to do this all with the ground in the loop. But right now, we're going to be doing this with all of the data and the commands being sent from Earth. In order to do this, we have to fly deformable mirrors. So these deformable mirrors have a bunch of tiny little actuators that basically can bend the surfaces to basically put patterns on the deformable mirrors to counteract any optical aberrations that appear in the system. We've never flown something like this in space and really understood how well it can operate in space, so that's something we'll need to be able to do. We're also flying these next generation chronograph masks. So you can see, maybe you visualize the chronograph to be like a dot that we put on an image, and that does everything. He blocks out the glare of the star and all that stuff. And that's kind of true for the previous generation. For the next generation of chronograph masks, they have all these very artistic patterns drawn into them. This is the result of very sophisticated optimization algorithms, optical design optimization algorithms to basically maximize planet sensitivity while also mitigating the diffraction of the star. So this is not done just to make it look cool. This is done as a result of very careful optimization of every one of these little pixels that become and correspond to these masks. We also need what's called EMCCDs, basically ultra low noise, no read noise, essentially no dark current CCDs, because not only are these exo-Earths at 10 to the minus 10 contrast, they're about at a Vmag of 30. So these are extremely, extremely faint things. And we want to talk about doing spectroscopy of these planets. Every photon counts. So we need to be able to count every photon and be limited by photon noise and nothing related to the detector at all. Yes?
Very briefly.
Yeah.
I don't know how coronagraphs work.
Yeah.
Where exactly do you place the coronagraph?
I completely skipped this in the kind of just to simplify things. But in the optical train, after we correct for the optical aberrations, the chronographs are placed in a series of focal and pupil planes depending on the design of the chronograph.
So it's way inside in the optical path.
Way in the optical path, yeah.
And it can still get rid of all the diffraction.
It can still get rid of all the diffraction.
That's the part that's kind of surprising to me. Okay.
We have that part. I think is the least concern of all of these things we are worried about right now. Yeah, the thing we understand is if you have a perfect wavefront, how our chronographs perform. It's just when you have an imperfect wavefront, how our chronographs perform is a hard part. But that part is actually okay. Yeah.
Another quick question.
Yeah.
For images that you show in the center there, how would Roman be able to switch between them? Is that what you're showing us? That there would be 4 possible?
Yeah, yes, exactly. So basically these live in a pupil plane, and you can basically place a filter wheel there, and you can basically move through all these various masks. I'll show you the dice. I'll show you the optics in a second. But first, the Roman chronograph is a technology demonstration first and foremost, but we're also going to try to do interesting science with it. With its capabilities, in particular, I'm excited about the fact that we can potentially get the first images of exoplanets in reflected starlight. And also, we can maybe obtain the first visible light images of exozodiacal dust. So our solar system, even the Earth, has zodiacal dust. It's basically dust that's in the same orbit as us. And this dust, depending on in other exoplanet systems, we don't know how diffuse or concentrated it is. If an exoplanet system could have exozodiacal dust that looks like on the right or on the left. On the left, this is going to make the detection of planets a lot more difficult, because not only are you seeing scattered reflected light of the star off the surface of the planet, you're also seeing reflected light off of all this exozodiacal dust that we're going to have to discern and filter out. So we'll get the first images of this exozodiacal dust to really understand, what do these the dust environments around these terrestrial planets of other stars look like. So the Roman chronograph is being assembled and tested right now. So here is actually where all the optics fit together. So this is all the optics. They've been assembled and aligned together. So the light from the telescope comes out from here, and it goes through this very complicated path of light that I've drawn by hand in PowerPoint, so it's not the most accurate. But we have first it goes through 2 deformable mirrors to correct for the wavefront aberrations. Then it goes through 3 masks, and these 3 masks are our chronograph masks. So it goes through 1, 2, 3. So this series of optical masks comprise our chronograph. A chronograph isn't just a single mask, it's a series of optical elements that are put together. So these 3 masks then block out the residual diffraction of the star, and then it finally goes through our filter wheel before it goes to the camera. We're doing this all in the visible, so our filter wheel it actually is visible light filters, so you can they actually look pretty cool. So this is just an image of our filters. You can actually see, these are actually just colors that we recognize. They're not some like weird. This is not some like this is not false color image or anything else. This is just the picture of the filters. All of this has been put into a black box. That is the optical bench here. Behind it is the electronics, and we also have a telescope source simulator. This was done at the end of last year. This was done in in-air testing just to make sure everything works together. Right now, as we're speaking, all of this stuff is in a vacuum chamber at JPL. There's no pictures of it because it's in a vacuum chamber, but it's being tested right now as if we're in space, because these optics are not designed to be operated in air. In air, things just don't work, basically, the way you expect it to work. These are all designed to work in a vacuum chamber, and all of these electronics and various optical components are being tested right now. Yes?
Over what delta lambda will this coronagraph give you the 10 to the minus 7, 10 to the minus 8?
That's a great question, and that's something we're going to have to figure. Like, we don't know exactly what the actual performance is, but we're aiming for something like 20% delta lambda. If we can. There's always I don't know how much you're familiar with these chronograph designs, but there's a trade-off always with delta lambda and how deep you can go. So maybe when you go to, yeah, but it really will depend. But a 10 to the minus 8 is a different regime than 10 to the minus 10, which is a different regime than 10 to the minus 6. So we're really kind of figuring things out as we go. And a lot of this stuff it's some part of it's an engineering problem as much as a science problem. So sometimes you don't really know from first principles. It's really practically how well can we operate things from a total systems engineering point of view. Mm-hmm. So this is all done now in a very community-driven fashion. Because it's a technology demonstration, there's not a big full-time staff supporting the chronograph. A lot of what we're going to be doing is going to be done from this community team that was solicited last year. It comprises of folks from various US universities and other institutions, plus our partners in Japan, MPIEA, France, and ESA that have also contributed various parts to the Roman chronograph. So this team of folks, we're going to be basically selecting targets, planning our observations, and analyzing the data. This includes commissioning the instrument. This includes developing the data reduction pipeline, planning which targets we're going to observe. Our primary goal was to demonstrate the technical capabilities of this instrument, but probably we also want to accomplish science goals as well. And probably the best way to demonstrate that your instrument works and achieves the technical goals that you want to achieve is to observe an interesting science target, detect a giant planet and reflect the starlight, and show that we can actually achieve the sensitivities which require to achieve those wavefront precision and detector specifications that we wanted to achieve in the first place. So we're trying our best to basically balance the primary goal of hitting these technology objectives with also making the data also have scientific value as well. If things don't go well, there's always a potential for extended science operation. And part of the kind of design of this community-driven program is we're funded to do this, but anyone is also welcome to contribute. So other folks have ideas for targets, other science cases we could do, other things we should consider. That's all open, and there's ways to join our community if you're interested. So that's kind of looking really far into the future in some ways. But let's go back to kind of the present. And in the present, we're mostly focused on imaging giant planets at beyond 10 AU. So these are planets 1 to a few times the mass of Jupiter at orbital separations beyond about 10 AU or so. And I think this is interesting because although from this plot you see that there are thousands of planets, why do we care about just a few over here? If I change this plot and only plot planets with quote unquote spectral characterization, that plot looks like this. So even though we've discovered thousands of planets, we haven't followed up that many of them. This plot is very out of date because I'm sure JBST has followed up many more planets that aren't in this plot right now. But the general phase space kind of remains the same. You have these close-in planets that we've characterized with unresolved spectroscopy, and then you have these very far-out planets that we've characterized with direct imaging resolved spectroscopy. And I'm going to focus on what we're trying to learn about planets out here. One of the things is you can think about is how did these planets out here form? They're all much more massive and much more further away than the giant planets in our own solar system. So we think giant planets naturally form through something called core accretion, where you form a massive rocky core, and then once that rocky core becomes massive enough, it'll start accreting enough gas that kind of undergoes runaway accretion to then form a giant planet. So that's that's how we think our own Jupiter formed. That's kind of this canonical model of core accretion. But for some of these really massive planets at really large separations, gravitational instability in the disks can also form these giant planets. This is when you have a disk that's massive enough, that's cool enough that the gravity overcomes the pressure forces and basically directly collapses and forms a giant planet without having to first accrete a core and then accrete a core that's massive enough to undergo runaway accretion or something like that. And we want to try to tell the differences between these two things. So for exoplanets, we have numbers. So one thing we can do is just count up the numbers of giant planets and how often they occur. And we can use occurrence rates to kind of distinguish giant planets from something like brown dwarf companions. And we think that in general, giant planets are more common than brown dwarf companions. And this might be a sign that these have formed through different mechanisms, potentially. But because we're directly imaged them, like occurrence rate is not the only thing we can do. And in particular, when you only have a couple dozen directly imaged planets, it's hard to do very robust occurrence rate statistics when you're limited by Poisson noise. But instead, we also can look at other aspects. We can look at their orbital configurations. We can look at how eccentric are giant planets versus how eccentric are brown dwarf companions. And we're finding that these two eccentricity distributions are different and that giant planets prefer more circular orbits than brown dwarfs. We can look at their compositions. We can look for, because we can directly image them, we can obtain spectra. And we think that while core accretion, you should form more metal-rich planets. They should have compositions that are different from the star because of how they preferentially accrete certain things. Gravitational instability should generally form things because it's just gravity should generally form things that are roughly stellar in composition. And then lastly, we can also look at the rotation rates and see if that tells us anything with respect to how these planets accrete or how they form and things like that. Part of this is that all of these two things and a little bit of this all require spectroscopy. Spectroscopy of their atmospheres helps us understand these objects better. So that's something I've been working on at Keck using the Keck telescopes. We have this new project called KPIC. It's the Keck Planet Imager and Characterizer. And our goal with this is to obtain very high spectral resolution spectra of directly imaged exoplanets. So what exactly is KPIC? It's not really a new instrument. It's actually a bunch of upgrades we've done to the existing Keck instrument suite. So this is a very cartoon, blocky optical diagram. But here's the Keck 2 primary mirror. This is the adaptive optics system at Keck. It's been there since like the early 2000s. And what we've done is that we've added a bunch of new optics in there that we can take the light from the adaptive optics system and in particular use this thing, what we call a fiber injection unit, or FIU, to basically isolate the light of a planet and feed that light through a single mode fiber into this high resolution spectrograph called NIRSpec. And what this allows us to do is obtain about R of 35,000 spectroscopy in the near infrared of directly imaged exoplanets. We've been working on this instrument for initially just as basically a technology demonstrator, but things have been working pretty well science-wise now that we're working on facilitizing the instrument right now, and it should be open to the broader community starting the next semester of 2024B. So why do you want to go to high spectral resolution? is that at very high spectral resolution, you're really resolving individual molecular absorption lines in these planets' atmospheres. And by spectrally resolving them, we can start to learn some things. We can, as the planet is moving towards or away from us, these lines will be Doppler shifted. So we can measure the radial velocities of the planets themselves. So not the radial velocities of the stars because of the wobble. We're measuring the radial velocity of the planets due to their orbital motion. As these planets spin, their molecular absorption lines get rotationally broadened, and we can measure that broadening to then infer what kind of rotation speeds these planets have. This is something that's only possible probably for the very brightest brown dwarf companions, and not really for planets so far. But if this is something similar to stellar like Doppler imaging, so that if you had features instead of star spots, to say clouds on the surfaces of these planets, they would block out patches of the planet's surface and alter the line, the shapes of the molecular absorption lines on the surface, and then you can kind of map out like particular clouds or cloudy spots or hot spots on the surfaces of these planets. And also, by measuring various like how the depth of these lines and which lines even exist in planets' atmospheres, you can measure their compositions and the general what these planets are made out of. And one thing you might have seen in the field of exoplanet high-res spectroscopy, if you follow it at all, or maybe if you don't, we oftentimes have to use what's called a cross-correlation function. And this is because planets are very faint. So when you disperse it into a high-resolution spectrograph with tens of thousands of spectral channels, you only have a few photons per spectral channel of the planet. And it's really hard to see each of these individual molecular absorption lines when you only have a few photons of the planet per channel. So what we have to do in order to kind of confirm that we've actually detected a planet is we use some template where we know roughly, we think this planet has carbon monoxide, so it should, the lines at about 2.295 microns should look something like this. And basically we multiply the template, which let's call teal, with the data, which is in orange, and we kind of shift the template in radial velocity space. And when the template is shifted to match the lines, the patterns that we actually see in the planet, you actually get a peak in the cross-correlation function. So here, the lines, when they're not shifted, they don't add or subtract constructively, so they kind of averages out to 0. And then when all the lines kind of line up, they basically get like constructive interference in some ways, and you get a peak in the cross-correlation function. So we often see things like this cross-correlation function to basically show that we've indeed detected the planet in the various template case we want to look for it. Although I'll show you in a brief moment, this is not actually how we analyze the data, but it's nice to kind of visualize our detections in this way. Okay, one thing I did mention is we use this thing called a single mode fiber, and you're like, why are we using a single mode fiber? So this is why we're using a single mode fiber. So there's conventional slit spectrographs, and conventional slit spectrographs are good in many cases, but not in the high contrast case. When we're trying to, so this is an image of a star that has 4 planets around it, and technically, if there was no glare of the star, you would be able to see them in the image. This actually is one of the images that made one of the movies I showed earlier. But without post-processing, this process of like us doing stuff after we acquired the data, you can't see the planets. And in fact, if you put a slit here at the location of one of these planets, you're getting all of this starlight into your spectrograph and also a little bit of planet light. And that's a lot of starlight to sift through, even just from a stellar photon noise perspective. That kind of limits your sensitivity. So instead, we use these single mode fibers, which we can build to match the exact size of a diffraction limited point spread function, and place it at the exact location where we expect the planet should be. And this allows us to only couple in light at this particular location relative to the star, so that we're getting in a lot less starlight than planet light, so that it's a lot easier to detect the planet. There's also other interesting properties that I'm not going to go into, but you can ask me the questions, because these single mode fibers are waveguides, and we can actually have very interesting controls of the electric field that allows us to do other interesting things. But this is how generally our instrument works for directly imaged planets. So we have a fiber tracking camera, and we have 4 fibers on our tracking camera. And what we want to do is put one of the fibers so that it's aligned with the planet that we're trying to observe, and then the other 3 fibers kind of sample the field of view and get us some independent starlight-only spectra that we can use for calibration. As you can see, this is not easy. We can't see the planet in our tracking camera images. What we have to do is basically have a known orbital ephemeris of the planet, have a good enough astrometric solution for our tracking camera that we can actually blindly offset the star relative to where we know the fiber should be, so that the planet light is injected into the fiber that we see here. This took a lot of work, but we can now basically do this offsetting to within 10 milliarcsecond precision, and that's generally good enough for us because this results, any misalignments at this level results in losses in throughput of less than 10% of planet light. So we're getting at least 90% of the planet light that we should expect to be getting in with our offsetting strategy that we're using here. This is how the data looks like on our spectrograph. It's a shell-based spectrograph. So here's one order, wavelength goes from left to right, and a second order, wavelength again goes from left to right. Here are 4 different fibers. There's one fiber. This is the fiber with all the planet and star light. This is the one we care about, but then you can see we also get 3 other fibers of spectra that we can use for calibration with just only starlight. This is how we actually reduce our data. We combine high-resolution spectroscopy techniques, but also with high-contrast imaging techniques that we're familiar with from our field. And essentially, we just fit the data in data space. So on black, this is our spectra that we obtained from that one red fiber. That spectra has a combination of residual starlight leaking into that fiber plus planet light. And what we do is we actually build a model that's a linear combination of 2 things. One is we have some astrophysical planet models that we use, and we try a bunch of them to see which planet model best fits the data. And then we also build a linear combination of empirical measurements of the star spectrum that we obtained and figure out which combination of star spectra we obtained best in combination with planet model spectra best allows us to have the best fits to the data. So this is actually what we're fitting. And this gives you a sense for, even with adaptive optics, starlight suppression, single mode fibers, the star is still much brighter than the planet. So we're still working on we basically have to spectrally filter out the star because the star has different absorption lines than the planet to distinguish the light of the planet from the light of the star. And although this is how we fit the data, it's still nice to then bring this back to the cross-correlation function. There are some statistical equivalencies you can do basically, but we can basically redo that plot, but in this space. And this shows us that basically at the radial velocity shift that we expect, for these 4 planets in that first movie I showed with the 4 planets orbiting each other, we detected all 4 of the planets at very high spectral resolution for the first time. We can detect both water and carbon monoxide in their atmospheres. And, so I'll get back to that in a second, but we also can measure the rotational broadening of these lines and basically measure their spin speeds. So we've measured the spin speeds of these 3 planets. What we actually measure is V sine I. So we don't actually measure V, we measure V sine I. So then what is sine I? Sine I depends on the inclination axis of the planet. And we don't know very much about planetary obliquity. Some folks are making some progress, but I think it's a very hard thing to measure in general. But you can make kind of 2 limiting assumptions. One is we can assume that the obliquity of the planet is aligned to the orbital axis of the planet. Maybe you don't believe in that. But then you can also just completely assume that the planets are completely randomly oriented in space. And in both cases, you can make some assumptions on how fast these planets should be spinning relative to their breakup velocities. And in addition to these planets, there are also higher mass planets that have also been observed. We've measured V sine I's for, as well as our own Jupiter and Saturn. And when we put that all together, it kind of looks like there might be a mass dependence. Although if you block out Jupiter and Saturn, this blob here just looks a lot less significant than when you add these 2 points. So one of the things we're trying to do with KPIC is to actually, because we have this new high contrast capability, is to detect more planets in this 1 to 10 Jupiter mass range to populate that part of the diagram to see, even without Jupiter and Saturn, do we see some trend here? Because we generally think that planetary magnetic fields regulate the spins of planets at very early times. But if there is a mass dependence, that might tell us that somehow this regulation is less effective for low mass planets in some way. And that'll be interesting to try to understand. Question?
Yeah, I'm just trying to understand that.
Yeah.
The spectrals
Yeah.
35,000.
Yes.
Corresponds to a velocity resolution of 10 kilometers per second.
Correct.
roughly speaking.
Correct. That's correct.
So I'm just wondering how you get down to a fraction of 1 kilometer per second.
Sorry, this is mislabeled. I should. That's actually my bad. This is a fractional velocity. So this is the velocity relative to breakup velocity. So this is actually my bad. So the actual velocity is about 15 to 50 kilometers per second is what we're actually measuring. Yeah. Yeah. Okay, so yeah, so we're trying to fill in this space and try to really understand if there is this rotational dependence with mass. Another thing we can do is try to detect molecules in the atmospheres of these planets. So these are the 4 planets, B, C, D, and E. And we can try to detect for things like carbon monoxide, water, methane, and try to look to see if we see their spectral signatures. And you can see that for some of these planets, for some of these molecules, we do detect them. But this is just detection. So the next question is, how do we go from these detection plots to actually measure abundances? And that's a bit trickier, and it requires you to have belief in your models. Because like I said, we don't actually see the spectra of these planets individually. We have to fit some models of these planet spectra on top of some empirical models of the star spectra to then infer some properties of these planets' atmosphere. Because these planets, each individual spectral channel only has so many planet photons. It's really noisy. It's kind of hard to actually see the actual high-resolution spectrum. So the first thing we've actually been doing is actually trying to actually measure the atmospheric composition of benchmark brown dwarfs. So benchmark brown dwarfs are these high-mass brown dwarfs with known masses, but more importantly, they have the same temperatures as these directly imaged planets, so the atmospheric physics are the same, and they orbit sun-like stars. So in general, we think these benchmark brown dwarfs have, just like binary stars, have roughly the same composition as their primary star. We can measure the composition of the primary star. We think, at least we think we understand it because these are sun-like stars. It's probably the best things we can measure composition-wise. And then we can try to measure these brown dwarf spectra from our high-resolution near-infrared spectra and see how closely they match. And you can see here for measuring the carbon to oxygen ratio, the stars in black and the planet is in the histogram of the planet's measured properties are in light blue. You can see that for carbon to oxygen, carbon to hydrogen, oxygen to hydrogen, we're doing pretty well. And in particular, it's roughly to about 20% accuracy, like 0.2 dex is how well we think we can do for this kind of particular case. And that's pretty good. I mean, I think we can do a lot already at that. We're better than order of magnitude. And one nice thing in particular about our very high resolution spectra is that we're oftentimes agnostic to clouds. So here's another benchmark brown dwarf where we try to measure the carbon to oxygen ratio, the C to H ratio, with different modeling assumptions. We use different cloud models. We often use the most extreme case where there's no clouds at all in the atmospheres of these planets. And we generally believe there should be clouds. And in all of these cases, we're actually able to measure the same composition, even though we've used completely different model hypotheses. And this is because when you go to very high spectral resolution, not only do you see the continuum, which is usually produced very low, deep in the planet's atmosphere, sometimes below the cloud deck, we also resolve the cores of these lines. The cores of these lines are much fainter. They're produced at cooler altitudes higher up in the atmosphere. And they're actually, the cores of these lines are formed high up above the cloud deck. So we believe the cloud deck for this particular planet is somewhere down here. And the cores of the lines that we can study are actually up here, and they're actually separated in altitude from the clouds. So that allows us, I think this is why we think that why our compositional measurements that we obtain here are independent of our cloud assumptions. So building off all of this, we've been undertaking this kind of high-resolution survey of substellar companions. So not only are we looking at planets between 1 and 10 Jupiter masses, we're also looking at their analogs, higher mass analogs between 10 and 100 Jupiter masses, these brown dwarf companions, and looking at things from 3 AU all the way out to hundreds of AU. and really spanning some, we believe at some point core accretions can't be efficient anymore. So as some of these objects probably formed through core accretion, some of these objects probably didn't. These are probably gravitational instability. But out to these very large distances, how did these large massive companions out here form? Did they form through disk instability? Did they migrate out here? Did they form through something else like direct cloud collapse from the NATO cloud? We're not quite sure. So we have this kind of survey that we're building up. The first step in our survey, we just wanted to analyze just a subsample. So this is just a subsample of objects kind of right at the boundary between all of these different various formation channels. And we wanted to try to see, does this sample show us anything interesting? And what we're finding right now is that this sample is actually very homogeneous. This group of objects somewhere between the mass of, someone has the mass somewhere between 10 and 30 Jupiter masses, they all have compositions consistent with solar, which is kind of what we expect from the gravitational collapse, direct gravitational collapse hypothesis. So it doesn't rule out that you could have some really extreme core accretion that just happens that at the end you end up basically accrete so much gas that what initially would be a metal-rich atmosphere is diluted with so much hydrogen that you end up with basically effectively a solar metallicity object. But I think it's also pretty, I would say the primary hypothesis we'd still go with is that these objects, because they're so consistent with solar or stellar, is that these form through direct gravitational collapse. In addition, these objects, with some of these objects, we're not measuring just C to O and C to H anymore. We're getting high enough signals noise in our spectra that we're actually measuring other things like 13CO. This is the isotopolog of carbon dioxide of carbon. And we can actually measure, detect both 12CO, which is the nominal isotopolog, and also 13CO. And we can actually measure the ratio of 12 to 13CO for these objects, as well as some other objects that have been previously detected with other instruments. I feel like this is somewhere where the data is ahead of the models, so we're not sure what we'd normally expect from theory, but since we just happen to get high enough signal noise spectra anyways, we're just starting to collect all of these measurements, and maybe as we get more of them, there'll be some interesting trends that start appearing. Okay, so that's kind of what we're currently doing, but we're also, like I said, KPIC is a testbed instrument. We're doing technology demonstration, and in particular for relevance for habitable worlds, is that what I talked about before for habitable worlds observatories, how can we get to habitable worlds through space? But also folks are thinking, how can we get there from the ground with the ELTs? So here again is the current generation of high contrast imagers in this flux ratio as a function of angular separation space. If you were to just port the existing technologies of these instruments and move them exactly as they are to the next generation of 30-meter class telescopes, our sensitivities would be up here. This is where we'd be. However, we kind of know from fundamental noise limits, we in theory could reach all the way down here. And this is where we want to be, because here is just a hypothetical population of simulated planets. And in green are temperate Earths in roughly the habitable zones around other nearby stars. And if we can reach about 10 to the minus 8 contrast at about a few tens of milliarcseconds, we can actually access the habitable zones of M dwarfs, nearby M dwarfs. But this requires us to go from here down to here. And just imaging alone is a few orders of magnitude away from reaching that kind of sensitivity limit. However, folks have been thinking about if we combine imaging with a high resolution spectrograph, maybe that combination could get us down there. Because right now, high contrast imaging kind of gets us down to about 10 to the minus 4 at these very small separations. But if we use the high resolution spectrograph to kind of filter out starlight, maybe that'll give us another 10 to the 4 in sensitivity and get us to 10 to the minus 8, 10 to the minus 9 that we need to get to hit these green exo-Earths around temperate M dwarfs, temperate exo-Earths around M dwarfs. However, these kind of studies that have been happening right now, this is assuming the most ideal case possible. Photon noise limit, detector noise limit, like no systematics. but surely there will be systematics. And the question is, what systematics will there be? And that's what we're trying to answer right now with KPIC. So we've been doing lots of things where we try to go as close, as you can see, we're trying to go really close in, we want to go to really high contrast and really small angular separations. And we've been trying this with KPIC, is to basically see what's our sensitivity at really small angular separations. To give you a sense for scale, 100 milliarcseconds is 2 lambda over d. This is 2 diffraction elements away from the central star's core. So, here we're actually achieving sensitivities that have never been achieved before for other high contrast imaging systems. These curves here, these are the best contrast curves, sensitivity curves ever reached by the previous generation of high contrast imagers. And with KPIC, we're actually able to reach down to interesting flux sensitivity levels at 2 lambda over d with just a very old adaptive optics system in our high resolution spectrograph. But we actually are not hitting the photon or detector noise level. I'm going to talk about this more at the lunch talk tomorrow, but essentially what we found is that when we combine a high contrast imaging system with a high resolution spectrograph, weird combinations start appearing. In particular, the dichroics that we use in the high contrast imaging system actually create spectral fringing in our high-res spectrograph. That spectral fringing mimics the signature of molecular absorption lines, and especially that is limiting our sensitivity down here. And we think if we can remove that fringing by, say, wedging the dichroics, maybe picking different materials, changing the index of refraction in some way, we can actually go further down and eventually hope to reach this photon or detector noise floor that we've been trying to aim for. And that would be good because this is assuming we can do that, and we don't know where we are, basically. We've achieved the factor of 100, so this is assuming we can get about 10 to the 4. Right now, we've achieved a factor of a few hundred, and we think if we can remove the systematics, we can achieve a factor of 1,000 potentially. But we have to keep going deeper and deeper to find all these systematics that are hiding. Every time you go in order of magnitude, there's always going to be new noise tempoles that you've never anticipated before. So that's kind of also on the technical side what we've been doing with KPIC. How much time do I have left?
10 minutes.
Okay. In the last little bit, I'm going to talk briefly about optical interferometry with gravity. So here, we're using, instead of 1 telescope, we're using 4 8-meter telescopes with the longest baseline separated by 130 meters to basically achieve the angular resolution of a 130-meter virtual telescope in the near infrared to do very high spatial resolution observations. So this is kind of the basics for interferometry. So if you remember your double slit experiment, if you shoot a laser through two slits, if you close one of the slits, this is what the interference diagram looks like. But then this is like the diffraction pattern of a single telescope. This is like the area diffraction pattern. But then if you open up that second slit and then shoot the laser through both slits, what you end up getting is here. So instead of the first null being at lambda over big D, where D is the size of your single slit or single telescope, your first null is at lambda over little d, where little d is no longer determined by the size of an individual slit or telescope. It's determined by the distance between the two slits, or the baseline between those two telescopes. But interferometry is hard, and in particular, you haven't seen it done for faint objects until gravity, because the atmosphere. When you have light coming from a source, and it goes through 2 telescopes, that light goes through 2 different patches of the atmosphere. And because it goes through 2 different patches of the atmosphere, that light has traveled different distances as it bounces around through atmospheric turbulence until it hits the telescope. And the problem with interferometry is that unless you correct for that optical path difference, or OPD, you're not going to get coherent interference fringes. To get clear interference fringes, you have to correct for this optical path difference. And that's difficult because the atmosphere changes every millisecond. So essentially, you have to measure and correct for this optical path difference every millisecond. And when you have that, you're just limited to how many photons you can collect from an astrophysical source before you have to make a correction. And that's why fringe tracking, even on 8-meter telescopes, is generally limited to sources that are brighter than 11th mag or so in K-band. That basically is all of the known directly imaged planets are much fainter than that. So what gravity does is that what I call reference star interferometry, they call it dual field mode. It's basically, they're able to have two interferometers. One interferometer is the fringe tracker that points at a bright star, say the exoplanet host star, and constantly measures and corrects for the optical path difference in the atmosphere. And they have a second interferometer point at the planet and use those corrections to maintain those fringes to then integrate for seconds at a time so that we can achieve down to a sensitivity of Kmag of 18. And this allows us to basically directly image exoplanets with interferometry. And that requires very precise instrument calibration that I'm not going to talk about. But with this, we're able to obtain the first detection of an exoplanet with optical interferometry. So this is, again, the 4 HR 8799 planets. We started with potentially the hardest one. We picked the innermost one. And here we detected it with interferometry. And just to give you a sense for how much more precise our measurement is, this is the orbit of the planet. If you zoom in by a factor of 2, you can see the error bars on the previous astrometry from regular 8 to 10 meter dish imaging. And then you zoom in by a factor of 200, that's when you can see the error bars from the gravity long baseline interferometry astrometry. So that's all gained from the fact of using a 130 meter baseline instead of an 8 meter baseline. So we detected quite a few planets, but I'm just going to give you a highlight one of them in particular. So this is Beta Pictoris. Beta Pictoris has it's this planet that lives in this edge-on debris disk. I did a whole chapter in my thesis on it. But with gravity, you can see because of how much more precise our astrometric measurements are, the eccentricity of this planet's orbit went from basically less than 0.3 to essentially known once we've obtained gravity astrometry on the orbit of this planet. What's more interesting is that radial velocity actually inferred an inner planet about 3 AU and 9 Jupiter masses from this planet, mass of 9 Jupiter masses at a separation of 3 AU. Because we know the system has an edge-on geometry, and we assume that this inner planet is coplanar with the edge-on geometry, we can basically image this radial velocity planet when it's at maximum elongation, because we know the orientation of the orbit. And this allowed us to get the first direct detection of a radial velocity planet using long baseline interferometry. We basically knew that the planet would be at its maximum elongation at this time, and we pointed our interferometer right there. And over the course of 3 epochs, we detected the planet. And even over the course of 2 days, we can actually measure the orbital motion of the planet. And what's more fun is that because there's an inner planet in the system, the inner planet causes the star to wobble because the star is going to wobble around the barycenter due to the gravitational pull of the inner planet. And what we measure with gravity is relative astrometry. So if you look at the outer planet, we're measuring the separation of the outer planet relative to this host star as a function of time. But if the host star is actually also being tugged on by the inner planet, this relative separation between B, the outer planet, and the host star is a combination of the orbital motion of the outer planet plus the wobble of the star due to the existence of an inner planet. And this is essentially epicycles in the visual orbit of the outer planet. It's basically, this is what happens when you assume a barycenter for the system, and it's not what you think it is. It's the same thing, epicycles, that happens when you think of heliocentric or geocentric theory. But we can actually measure these epicycles. These epicycles have an amplitude about 1 milliarcseconds or so. And we can actually, over the course of a few years, through monitoring the outer planet's orbit, we can subtract off the Keplerian orbit of the outer planet. And in its visual orbit, we can actually see a second sinusoid as a function of time. That's due to the wobble of the inner planet causing the inner planet causing the star to wobble around the true system barycenter. And this allows us to use relative astrometry only with gravity to measure a dynamical mass of the inner planet, because the amplitude of this wobble is proportional directly to the mass of the inner planet. So we're able to actually measure a dynamical mass of 9 plus or minus 1 Jupiter masses just from measuring this. So that's been pretty fun. There's also been some other fun stuff, but I'm, in the interest of time, going to skip all of that. Yeah, we had lots of fun stuff. And then this is not something I am involved with, but because of, I think, partially the successes of optical interferometry, people have been, especially in Europe, are reviving this idea of doing long baseline interferometry in space, not in the near infrared, but in the mid infrared to look to eventually detect thermal emission from exo-Earths and doing atmospheric characterization and detection in the thermal infrared using formation flying and optical interferometry in space. Yeah, so that's, I know I went through a whirlwind of various things, but we talked about high contrast imaging, pushing the next generation of chronographs, but also doing high-res spectroscopy and long baseline interferometry characterization of planets. And hopefully in the future, from the ground or in space, we can use some of these same technologies to image habitable worlds. Thank you.
All right, thanks so much, Jason. We have time for questions. Yeah.
So in radio interferometry, people widely use this thing called closure phase. Is that something that's doable here?
That's a good question. So we sometimes use closure phase and sometimes we don't use closure phase. So in the things I showed you there, we don't use closure phase. We actually calibrate on the star itself. So instead of basically self-calibration. But in some other applications which I'm not discussing here, where we're like actually trying to like resolve the planet or like looking for binary planets and things like that, we do use closure phase measurements in those particular cases. Yes.
Any other questions?
Yeah, for the spectral analysis, of course, faint star stellar spectroscopy has advanced a lot in the last 20 years in terms of template fitting, and it seems like you're not quite there. Is that fair to say, or is it?
I think that's fair to say. There's been a lot more work in stellar spectroscopy than planet spectroscopy. I think planet spectroscopy in many ways is messier because we have a lot of molecules and not just atoms and molecules, especially things like even opacities for molecules at high pressures are difficult. And then another confounding factor for us is clouds, and partially why I'm motivated to go to high resolution is kind of we can maybe sidestep the influence of clouds and how to model them. But I think, yes, planetary atmospheric models I would say are developing, and they're developing fast and we're maturing, but I'd say in the last 5 years we've made a lot of progress, but we started from a very naive space probably 5 to 10 years ago.
Yeah.
How to determine the planetary mass found by the direct imaging method?
How do we determine the planetary mass from direct imaging method? That's a very good question. So a lot of the masses are not known. They're all a lot of the masses are model dependent, but we're trying to build up dynamical masses are the gold standard, and we're trying to get as many dynamical masses as we can. The model dependent mass is you see a brightness of a dot, and the brightness of the dot is correlated with the mass, but it's also correlated with the age. So basically, the brightness of the dot correlates with the temperature of the dot. The temperature of the dot depends on, basically we're looking at really young objects. These are self-luminous, so they're cooling over time. So you can have something that's massive and old, or less massive and young that all have the same dot. So you have to know the age of the planet. And from that, to do that well, you have to know the age of the stars. So there's been a lot of work to kind of age date all the stars of all the known directly imaged planets so we can accurately measure their masses. But over the last, I would say, 5 years or so, we've been attaining a good handful of masses measured dynamically, either through the radial-velocity method or through the absolute astrometry method with Hipparcos and Gaia. And that's been useful to actually give us gold standard dynamical masses, but also show us that the previous masses we've been inferring through our evolutionary models are actually not that bad. They've actually, all the dynamical masses generally are consistent with what we've been inferring through evolutionary models. So that's actually a reassuring thing for us that these masses aren't completely off that we're seeing.
Right, I have a question too, which is, are there maybe some of the slides that you skipped, but have you looked at other radial velocity detector planets with gravity?
We have. There's been a few cases. I think one case I skipped is there's a planet that's been indirectly inferred through both radial velocity trend and an absolute astrometry acceleration, and it's a number, if you care, is HD 206-893c. but this is like a 12 Joule mass companion at 3 AU that we would also directly image with gravity. But in general, I think I'll talk about this more at Pizza Lunch. We've been trying to push to smaller separations and use things like radial velocities and Gaia particle astrometry kind of guide us and point us where to look to try to detect these much more closer in planets that we haven't previously been able to detect.
All right, any more questions? All right, if not, let's thank Jason once more.
Thank you.